but just making sure that as many people hear it as possible. Okay? Evidently, I'm just sort of guessing at this, I think enrollment must be way low for spring. And the administration's gotten awfully panicky about it, it seems like, and maybe rightly so. I'm not making any judgment call on that. But I can't help but think that part of that is their own emphasis, or I don't know what's been going on. Let me give you a little background, okay? Last summer, the state, Alabama Community College system, forced everyone in the system to go to this new management package called Banner. There's nothing wrong with Banner, but it's just a brand new package, very different from what most people have been using before. They wanted everybody in the system to be on the same package. And admittedly, the old system we had been using was a political boondoggle from a past chancellor who is, I think, maybe in jail now. I don't know. He was a crook, but it was an ancient system, and we had hung on to it for way too long, but nobody wanted to change. So it wasn't a bad move going to Banner, but doing it at the time of COVID-19, when no one's on campus, or they weren't on campus at the time, and having to learn this new system, all doing it remotely. The students are remote, everyone is remote, and Banner is different. One of the differences in Banner is a faculty member cannot register a student. The students have to register themselves, which is fine. There's nothing wrong with that, but you don't have the one-on-one that we did when we were on campus, so we could help people walk through it and that kind of stuff. So last summer they came up with this concept of a virtual advising center, and they really pushed it, and they were always sending emails, go sign up and stuff like this. And I was signed up, I don't remember how many hours, something like maybe 6 or 7 hours a week. Whatever time I had free, I was listed as an advisor for those hours. And as it turned out, just about every 30-minute slot that I was listed in those 6 to 7 hours, almost every week, almost every 30-minute slot was filled up. I mean, I just had advisees out there all the time. And I was advising them, and once they got advised, then I sort of explained to them, how to register and all that kind of stuff. People were able to do so. Okay? Now, we had pretty decent enrollment in the fall. Of course, most falls are our highest time. But a couple of things. Banner was also different this way. If a student hadn't shown up in class in the first week, it kicked them out. So we went to great gory detail to try to make sure all the students knew they had to show up the first day of class or turn in an assignment or something like that. Y'all probably remember that as well. And that seemed to do okay, and then they managed to manipulate the system somehow and get some of those students who hadn't shown up, made sure they got back in, and okay. Then they had, and this was true in the previous package as well, anytime a student who had paid for a class had not shown up, now they were taken out that first week, but then they went through it again and removed students who had never shown. Well, that shouldn't have been many. And then at some point they removed students who hadn't paid. Now there's a big difference there. Banner, we the instructors cannot tell if a student's paid or not. In the old system, we could tell. There were little subtle ways we could tell if a student had paid or not. Asterisk by the name, not showing up on this list when they were showing up on the other list. There were ways we could tell. But in the Banner system, we can't tell. And I think the administrators had a hard time telling. Of course, the financial people they knew, but that was about it. Well, we lost a big number when they purged the system from people who hadn't paid. Well, I don't know what happened, but this term I've been down all term long for 5 hours a week for virtual advising. Okay, a lot like last summer, I had 6 hours, maybe 7. This fall I've had 5. This fall, I've had zero students sign up for virtual advising. Now, I don't know why. It may be because I'm retiring and they're sending all the students to people who will be here in the spring. I doubt if that's the case, but it could be. But then, too, on the other hand, I don't think they've been publishing that. See your virtual advising, sign up for virtual advising. And it's because they haven't been pushing that, no one's signing up for virtual advising. Well, if they don't sign up for virtual advising, guess what? They may not be able to register, because I believe Banner System also prevents you from registering unless you've been advised. So now they're panicking because they don't have enough students signed up for the spring. Well, what they're doing as a response to that, which I don't totally agree with, but maybe students want this, is that they're having a big push next week, and they're advising students on campus from Monday through Thursday of next week, from 9 in the morning until 7 in the evening. And they will have people on both campuses in big rooms, big tables, plexiglass separators, doing everything as safely as possible. And of course, everybody, like we were talking about at Kelly's wedding, everybody in mask, that can be in mask, all this kind of stuff. They're making it as safe as possible, but they're encouraging all students who haven't registered to come to campus, get advised, so they can. Here comes Morgan. Let me get her in before I go any further. There's Morgan. Okay. So we should be up to 1, 2, 3, 4, 5, 6, 7, 8, 9 students. Is that all so far? Yep, 9 students. Okay. Morgan, I was just talking about what's happening next week. They're making a really big push to get as many students registered next week as possible. So they're going to have faculty members on campus, which we haven't been because we're teaching remotely. They've been forcing most faculty members to be on campus 2 days a week, Monday, Wednesday, or Tuesday, Thursday, unless for some reason they can't be, like I can't be because of my health situation. And I can't be there next week either because of my health situation. But they're going to have faculty or staff or administrators or somebody at the advising tables on both campuses Monday through Thursday from 9 in the morning until 7 in the evening. Now, if the Birmingham campus is more convenient for you, you go to the Academic Success Center. That's that big new building right across from on Wilson Road, right next door to what is Winona School. I don't remember if it's next to the high school or the elementary school. I think it's the elementary school, but I'm not certain. But right there at Winona, right next to that is, in fact, it used to be Winona. That plot of land was Winona Elementary, but they built a new building for them further down, and that building became ours. They tore it down and made a new advising success center there, student success center. So that's on the Birmingham campus. On the Bessemer campus, it's in the Ethel Hall Auditorium. Now there's an Ethel Hall also on Birmingham East campus. That's not what we're talking about. We're talking about Ethel Hall Auditorium on the Bessemer campus. So that's where you go if you need to be face to face with plexiglass and mask in between advising. Go to one of those 2 locations anytime between 9 in the morning and 7 in the evening on either campus, Monday through Thursday of next week. If you'd rather not be on campus, please sign up for virtual advising today or tomorrow. You can get your advising done virtually, get it knocked out, get your registration done. You don't have to go to campus then. But if you really want to go or need to go or feel the compulsion to go or something, then please go next week. Okay, but I'd rather that you do virtual advising. That's a lot safer and healthier. Okay, but get advised and get registered next week if possible. All right, any questions on that? Okay, I heard some dings going on. Yeah, we still got 9 students, so I don't think anyone else has joined. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it. All right, then where we are in trig, if there are no more questions, we're in chapter 5, analytic trigonometry. We're in section 5.4, which are the sum and the difference formulas. We talked about those, we started those, and we're on page 375, example 4, near the bottom of page 375. This is not on the PowerPoint, so that's why we're starting on the white page. Okay, and here's example form. Example 4. I said form, I don't know why. Write this expression. Okay, cosine of arctangent of 1. I prefer to use inverse tangent, but the book has arctangent, so I'm going to write this down. And this pen is not operating well at all today. It did pretty well in the first class, but it's not doing well now. 1 plus arc cosine of x, it's supposed to be an r, okay, close parentheses, as an algebraic expression. So write that expression as an algebraic expression. Now, that's pretty ugly. I'm going to try to clean that up a little bit. If I can get my pen to show up where it needs to be. Okay, so that's the arctangent. That came out better. This is arc cosine. That was a plus sign. It made it look like a. All right, hopefully that's a little more readable. Okay, now I don't know specifically where the book wants you to start with this, but I'm going to tell you how I would approach this problem. Now, and I do this with any time they have inverse or arc functions. You know, they're the same thing. They mean the same thing. Okay, I say, what does this mean? Well, when you're taking a cosine or any trig function of something, you're taking that of an angle. Now, the book doesn't like to focus on angles. I like to think in terms of angle. Okay, so this thing had better be an angle, and this thing had better be an angle, because you're taking a cosine of the sum of 2 angles. Okay, we'll get to that in a minute. Okay, so basically what an inverse or an arc trig function tells you, this represents some angle. Okay, I like to call this maybe theta. Okay, and maybe this one, my arc disappeared again. This arc cosine, that represents some angle. Well, we've already used theta, so what's your next favorite Greek letter? I don't really care. Give me a Greek letter. Anybody? Nobody knows the Greek letters. Okay, if you don't, that's okay. Let's use alpha. Okay, call alpha. No, that's something else. Now, how do you write this? How you write this in a different form would be that tangent of alpha, because you take trig functions of angles, is equal to 1. That's what this. If this thing right here, arctangent of 1 is equal to theta, that means tangent of theta is equal to 1. Plus, and if these are equal, arc cosine of x is equal to alpha, that means that cosine of alpha is equal to x. Okay? Now you ask yourself, okay, what angle theta, because that's what we're looking for here, for right now is that angle theta, when you take the tangent of it, is going to be 1. Hopefully somebody knows that, right? What angle theta, when you take the tangent of it, do you get 1? Nobody's answering. Well, if you're thinking in terms of degrees, that would be 45 degrees. In terms of radian, that theta would be pi fourths. So this theta is pi fourths, if the pen would write. Okay, now this is a little tougher, okay, because you don't have a an expression here. It's not actually a number, it's an expression. Okay, now what I'm going to do is represent this with my famous little triangle. Okay, if this is the angle theta, alpha, angle alpha, and the cosine of alpha was x, that means cosine is adjacent over hypotenuse. This would be x over 1. Okay, so the cosine of alpha would be x over 1. So let's just write that. Well, cosine alpha would be x over 1. So just hold off on that for a moment. Okay, now what then would be cosine of, now we've already determined this theta, this part right here, has got to be pi fourths. The pen's not writing. Plus, and this is just going to be inverse cosine of x. So I'm just going to leave it written like that. Or I'll actually write it, because they did, arc cosine of x. But just remember, this is up there. Okay, that's all we had to begin with. It's all we got now. Well, how does this run? The cosine of a sum is cosine pi fourths times the cosine of arc cosine. I should have 2 C's in there. I hate writing arc cosine. I like to write inverse cosine. Minus the sine of pi fourths times the sine of arc cosine of x. Okay, now this is why the little triangle comes into play, because you know that this squared plus that squared has to equal 1, right? So that means this side over here that we don't know has to equal 1 minus x squared. So this side here is 1 minus the square root of 1 minus x squared. Okay, Pythagorean theorem. This squared plus that squared is equal to 1. And if you square this, you get x squared. Square this, you get 1 minus x squared. X squared minus x squared is 0. So you get 1 equal 1. So that works. Now, I jumped the gun a little bit on that. Let's see what this is. Cosine of pi fourths is, hopefully you know that one, the square root of 2 over 2. Now, the cosine of an inverse cosine, now they didn't tell us anything about it, but I made the assumption this was an angle between 0 and pi halves. Actually, you could say between 0 and pi, actually, but we're going to stick with that. So this is just going to be square root of 2 over 2 times the inverse cosine cosine of an inverse cosine just leaves you with x. Minus, well, the sine of pi fourths is also root 2 over 2. Now, the sine of this angle, remember this is that angle alpha, there's that angle. The sine of that angle is opposite over hypotenuse. So this is the square root of 1 minus x squared. Okay, so what does that leave you with? Root 2 over 2 times x minus the square root of 1 minus x squared. Now, I don't know if that's the way they give their answer, but that's an expression. What was the question? Write that expression here. If I could get my pen to show up now. Come on, pen, where are you? There you are. Write this expression here as an algebraic expression. There's an algebraic expression. Now, whether that's the one they want or not, we'll see. Okay? And they, okay. What they did, they took it one more step. I don't know why, but they did. The square root of 2 times x minus the square root of and they multiplied the square root of 2 times this, square root of 2 minus 2x squared. I never would have thought in a million years of expressing it this way and putting all that over 2. That's how they wrote their answer. Guess what? It doesn't matter how you write it, okay, as long as it's correct. And both of these answers are correct. The thing that you have to keep in mind, this square root of 2 is, the x is not under that square root. This x squared is under the square root because it was under that one. Now, that to me is no simpler of a way to express the answer than that one. That to me would have won. That's how I would have left it, just like that. They took it that one more step, and that's fine. Actually, they went round their ear to get there, but it still works. Okay. Any questions on example 4? Okay. Most examples, just about every example, followed by a checkpoint. Please do the checkpoints. Okay. Now, I think example 5 may be done in the PowerPoint. Let's see if it is. Okay. This was example, yeah, there's example 5. I thought it was. Before we get to example 5, though, there is a little blurb in the left-hand column of page 376, that's where example 5 is located, on Hipparchus, considered the most important of the Greek astronomers, born about 190 BC in Nicaea, which I think is a town in Greece, credited with the invention of trigonometry. His work contributed to the derivation of the sum in different formulas, which is what we're doing now. So not only did he come up with these formulas, he actually came up with trigonometry in many senses. So if you haven't gotten a paper topic yet, hint, hint, please, here's a good one. Now this little blurb here cannot be your source, but it can be your source for ideas. Okay? So please, if you haven't submitted a paper yet, please get that done. If you get it done this week or next, or anytime this month, which you don't have much more time this month, you do get that one extra bonus points that's sitting out there waiting for you to use. But if you turn it in the month of December, you just get your score. No bonus point added. Okay. If you turn it in after the last day of class, which is the first Thursday in December, you start losing points. So please don't do that. Get it in sooner rather than later. Okay, another thing about example 5 is also at larsonprecalculus.com. There you can see an interactive version of this type of example. Here's what it says. They actually say more on the slide than they do in the book. It says verify, they say prove, doesn't matter. Cosine of pi halves minus x is sine of x. Now we know that as a cofunction identity. That's what it says there. The cosine of the complement of an angle is the sine of that angle. And this is the cosine of the complement, pi halves minus x, is the sine of x. But they say, prove it. Okay, don't just take someone's word for it, prove it. Well, here's what we're going to do. There's a difference formula, isn't it? So that's going to be cosine of pi halves times the cosine of x. You could have said minus x, but cosine of minus x is the same as cosine of x. Plus, remember, if it's a minus here with cosine, it becomes a plus down here. Plus sine of pi halves times sine of x. That's your cosine of a difference formula. The question is that equal to sine x? All right. Well, first question we ask ourselves is, what is cosine of pi halves? If you think about it, cosine starts at 1, and at pi halves it goes down to 0. So this is 0. And 0 times cosine x, that's 0. What is sine of pi halves? Well, pi halves, sine starts at 0 and goes up to 1 at pi halves. So this will be 1. So now we have sine x, 1 times sine x, and here's Sharika. Way to go, Sharika. She's here now. Let me mark her present. Okay, so we're turning out having a fairly good sized class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But at least we broke double digits. Okay. Yep, we got 10 students here. Okay. And that does show that, Sharika, we're on in Chapter 5, Analytic Trigonometry, Section 5.4, Sum and Difference Formulas, and we're on Examples 5, which is top of page 376, and that's here on the PowerPoint. And we just had shown that indeed sine x is equal to sine x. What we did was verify this identity, their cofunction identity, that the cofunction of a complementary function is a complementary angle is the same as the function of that angle. Done. There it was. Any questions on that? So what I'll do now is erase my scratch so you can see what's following here. So we use the cosine of a difference formula because that was a difference. The cosine of a difference is cosine of the first times cosine of the second plus the sine of the first times the sine of the second. So the cosine of the first is cosine pi halves times cosine of the second is cosine x plus sine of the first, sine of pi halves times sine of the second, which is sine of x. And here we see the cosine pi halves, because it's 0, that first whole term is 0. Sine of pi halves is 1, so 1 times sine x is simply sine x, and sine x equal sine x. Done. Any questions? Okay. Before we move to, let me see if I can find this. I do not see this in the book. I know it's there, but I don't see it there. Oh, there it is. I see it. Yeah. This is right under example 5. It's just sort of hidden there. Okay. Sum and difference formulas can be used to rewrite expressions such as this. Now that was what we have been calling a general solution or something like that. Sine of theta plus n pi over 2, or n over 2 pi, or pi halves times n, or something like that. Or cosine of theta plus n pi over 2, or pi halves n, or something like that. Where n is any integer, to rewrite those to get expressions involving only sines and cosines. And I'm sorry, but the anemia is hitting me pretty hard right now. Let me get a little something to boost some energy. In between the two classes, I ate a few almonds trying to boost it, but they've run out. So the resulting formulas are called reduction formulas. So this is a sum of a sine. Usually what we sort of see something like this when we're doing general equations. And so example 6, I think, is going to take one of these, maybe both of them, and show you how you come up with reduction formulas. So let's move on to not example 6, okay? So let me go back a slide, and we'll go to the whiteboard and do it there. Anyone need this left up here a little bit longer? Okay, I'll take that to be a no. And let's do example 6. Write each expression as a trigonometric function of only theta. So here's the second one from what we had before. Cosine of theta minus 3 halves pi. Theta minus 3 pi over 2. Now, your cosine of a difference, remember, is cosine of the first, which would be the cosine theta, times cosine of the second, cosine of 3 halves pi, and with a minus here for cosine, it becomes a plus here for your difference, and that would be sine of theta, the first, times the sine of 3 halves pi. All right, now cosine theta is cosine theta, so bring that down. Now, what in the world is cosine of 3 halves pi? If we remember what we were just doing before, cosine starts at positive 1. At pi halves it goes down to 0. At pi it goes down to negative 1. And at 3 halves pi it's back at 0. So cosine of every one of your half pi's is 0. So this is going to 0. So therefore this whole term will be 0. Okay? Plus sine of theta times sine of 3 halves pi. Well, sine starts at 0. At pi halves it's up to plus 1. At pi it's down to 0. And at 3 halves pi it's down to minus 1. So this becomes a yuck. Okay, that becomes minus sine theta. And this is called a reduction formula. Cosine of theta minus 3 halves pi is the same as minus sine theta. That should be your 6A, and that's exactly what they got. Okay, now this one's a little trickier. What it says, use the formula for tangent of u plus v to come up with tangent of theta plus 3 pi. Now, this requires you to remember what tangent of u plus v is. And let's do a quick review of that. That would be tangent u, which in this case is theta, same sign here, plus the tangent of 3 pi, the second one there, divided by 1 opposite sign here minus tangent theta times tangent 3 pi. Okay, so everything here is going to hinge on what in the world is tangent of 3 pi. Well, this will be tangent theta, because that's the same. Now, if you think about your tangent function, tangent of 0 is 0, okay? It goes down as you approach negative pi halves, it goes to negative infinity. Positive pi halves goes to positive infinity. Okay, so that gets you your vertical asymptotes at your half pi. Well, then you go to the next vertical asymptote, should be pi halves and 3 halves pi. Vertical asymptotes there, right in the middle is pi. Okay, then go again, and you get 3 halves pi to 5 halves pi. Right in the middle is 2 pi. Okay, go again, you get minus, you see what's happening? At the half pi's, all the half pi's, the tangent function is undefined. Vertical asymptotes. At all the whole pi's, including 3 pi, the tangent is 0. That's right smack in between that. So this will be plus 0 over 1 minus tangent theta times 0. So guess what? Tangent of theta plus 3 pi is simply tangent of theta. But wait a minute, we knew that, didn't we? Because the period for tangent and cotangent is pi. So every pi you have the same value. So since tangent of theta, whatever that theta is, go 1 pi over, it's the same value. Another pi is the same value. Another pi is the same value. So sure enough, we knew that one without having to do our sum formula, but using it, you found it to be true. All right, so that's example 6. They're followed by a checkpoint. Please do your checkpoints. All right, now we go back to example 7. We've still got 10 students here, which is pretty low for this class, but I'm glad y'all are here. Okay. All right, so those were reduction formulas. Let's do example 7 here. Find all the solutions for sine of x plus pi fourths. They have not written this well. Okay, this should have a bracket here. Sine of x plus pi fourths plus the sine of x minus pi fourths, and they should have a bracket there, is equal to 1 in the interval from 0 to 2 pi, including 0, not including 2 pi. That's a little on the sloppy side. In the book, they got it right. On the PowerPoints, they did not. Okay, whoever was doing the graphics sort of left that one out. Okay, so how do we solve that equation? That is an equation. It says find the solutions. This is looking for the values of x which make that true. Well, we got a ways to go before we can figure out what x is. Let's first use our sine of the sum formula and sine of the difference formulas to see what we can get here. So the sine of a sum is, I'm going to start over here because I think this is going to take a while. Sine of x times the cosine of the second one, pi fourths, plus, for the sine function, it's the same sign there, the same sign as here, cosine of x times the sine of pi fourths. Okay, that's what this one is. Plus the sine of x cosine pi fourths minus the cosine of x times the sine of pi fourths. Okay, and that's equal to minus 1. Okay. Now let's see what we've got here. Here we have a sine x cosine pi fourths. There we have another one plus sine in between. So that's going to be 2 times the sine of x. What is cosine of pi fourths? Cosine of pi fourths is square root of 2 over 2. So this would just then be the square root of 2, because the over 2's would cancel out, and that just leaves you square root of 2 sine x. Okay, so that's taking care of this term and that term. But then look at these two terms. This is a plus, that's a minus. The same two terms, those add to 0. So this is equal to negative 1. Well, obviously, what you need to do now is divide by root 2. Okay, and the root 2's go out here, and you're left with sine x is equal to, and if you prefer it this way, minus root 2 over 2. Okay, well, where are we, Waldo? Sine is negative only in the third and fourth quadrant. Okay, now sine is defined, the inverse sine is only defined in between minus pi halves and pi halves. So this is in the fourth quadrant, but it's usually listed as a negative angle. Okay, and what angle is that? Well, it's the same one we used here, is that the sine and cosine of pi fourths is root 2 over 2. So this implies x has to be minus pi fourths. Okay, but that's not in the same right interval. Okay, because minus pi fourths isn't between 0 and so this covers first quadrant, second quadrant, sine is positive in both of those, third quadrant and fourth quadrant. So this would be at x equal pi fourths beyond pi, so that would be 5 pi fourths, or 7 pi fourths. Pi fourths minus, short of 2 pi. Those are both in this interval. Okay, this is the same angle, that's a coterminal angle as that one, but this one's not in that interval, this one is. The other place would be in the third quadrant, because sine is also negative in the third quadrant, and that would be 5 pi fourths. Does that make sense? All right, that's example 7. Let's see what they got. I believe they got the same answers. So let's look and see how they did it. See if they did it any differently from what we did, or I did. Okay. Using the sum and the difference formulas, we rewrite the equation as sine of the first times cosine of the second. That's sine x cosine pi fourths plus this one. And I still get irritated that they didn't put the bracket in there like they should have, here or here. Okay, plus sine or cosine x times the sine of pi fourths. Oh, here's Courtney. Good deal. Let me get him here, if I can do that without dropping everything. So Courtney's here. All right. Still missing a few people today, but I'm glad y'all are here. Okay, let me check and see if I've got everyone marked. Yep, 11 students, and I'm pretty sure we're now up to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it. Okay, hopefully more will be coming in. We only have about 25 minutes to go. All right. So, Courtney, we're in Chapter 5, Analytic Trigonometry, Section 5.4, Sum and Difference Formulas. We're doing Example 7 at the top of page 377, and it's also on the slide set here. So we just had set it up that the sine of a sum, if I could get my pen to show up, is the sine of the first times the cosine of the second. That gives us this one, plus, same sign here, cosine of the first times sine of the second. That's this one, plus, because the plus is here, sine of the first times cosine of the second, minus cosine of the first times cosine of the second. No, times sine of the second, sorry. Okay? Now here we notice these two are exactly the same, so this gives us 2 times sine x cosine pi fourths. These two are exactly the opposite, so those add to 0. So this gives us 2 times sine x. Okay, here we go. Sometimes this works better. Right now it's not. No, there it is. 2 times sine x cosine pi fourths from those two is equal to minus 1 here, because those two add to 0. Okay? Now what we'll do next is divide both sides by 2. And then when we do that, okay. Cosine of pi fourths is square root of 2 over 2. Okay, so before we divide by 2, let's write that as square root of 2 over 2 times 2. The 2's will go out, and that gives you square root of 2 times sine x is equal to minus 1. And they show you plugging that in here, and that gives you, they skipped that step. They show you the easy step and skip the harder step, but it's okay. Sine of x is minus 1 over root 2, which you could write as minus root 2 over 2. Well, we know that sine of minus root 2 over 2 is either going to be in the third or the fourth quadrant, and it's going to be pi fourths as a reference angle, and that would give us x is equal to 5 pi fourths in the third quadrant, 7 pi fourths in the fourth quadrant. Okay, so that's the only two places in this interval from 0 to 2 pi where sine of x would be minus root 2 over 2. Make sense? All right. Now that's the end of the slideshow, but it's not the end of the section. So let's go back to the whiteboard. And does anyone need that any longer? I hope not. If not, I'm going to clear it. All right, let's do example 8. This is a longer, more involved problem, so let me get my book in my lap. So, oh, and by the way, following example 7, another checkpoint. Please do your checkpoints. That's, to me, the best way to reinforce what we just did. Okay, so here's a verification problem, and this is verify that sine of x plus h minus sine of x okay, and by the way, this is an application from calculus, divided by h is equal to cosine x times sine of h over h minus sine of x times 1 minus cosine of h, okay, over h, okay, where of course h can't be equal to 0, but in calculus it will be approaching 0. Okay? Now, for those, hopefully many of you will be continuing to do calculus. If you do, you'll see this is part of the process of taking a derivative of sine. Okay? So, with that in mind, let's get to work here. Okay, this is a sine of a sum, and that would be the sine of x cosine of h plus the cosine of x times the sine of h. Okay, that's what your sum of a sine of a sum formula is. That's it, just straight out of the book. Minus sine x and all that is divided by h. Now we're going to leave the right hand side alone for right now. We're just going to mess with this side. Okay? Now, what we're going to do is combine the two terms that have sine x in them. Okay, those are those two terms. So this will be sine x cosine h minus sine x, minus sine x, that's over h, and then we'll have plus cosine x sine h over h. We just took these two and put them together, and that one, and left it alone. Okay? Now, factor out the sine x. And what you have left is cosine h minus 1 over h plus factor out the cosine x times sine h over h. Now there's something later you'll see called hyperbolic sine and hyperbolic cosine. That's not what this is. This is cosine h and that's sine h. Okay, they're given the same thing. It's just that in the book they can italicize, I can't. So it's not quite as clear that these are functions. So I think what I'll do is I'll put them in parentheses here, so you know it's not a hyperbolic function. Okay, you haven't hit those yet, I don't think, or maybe you have. Now, I don't know why they did this, but this term is obviously the same as that term, so these two are the same. But what they did then is negate this, which meant they reversed these two. And that indeed gives you exactly that. Why they went to that form, I'm not sure. Okay? I would have left it in the form we had it, or put it in that form, because that is such a simple, it's just a simple form. Okay? Now you'll see once you get to calculus that this expression here, the sine of yuck, where in the world is the pen and why won't it show up? Okay, there it is. Okay, and now it has this showing up. I don't know. Okay. You'll learn in calculus that sine h over h as h goes to 0, believe it or not, is 1. And cosine h minus 1 over h, well, cosine h over h as h goes to 0 is 0. So this would give you a minus 1, I mean a sign here. And what that tells you in the long run is the derivative of sine is cosine. And basically later you'll do the derivative of cosine is minus sine. Okay, so you don't need to know that yet, but that's what it's driving toward. That's how they use it in calculus. All right, any questions on that? So anyway, you come up. There is a summary at the bottom of page 377. Always good to look at the summary, and that may lend you credence in answering the vocabulary at the top of page 378. Okay? There's 6 blanks here. Fill in the blank. Sine of u minus v. What would that be? Anybody? Sine of u minus v. Well, just by every one of these, you'll start almost the same. Sine of u, but with the sine, then you move to cosine v. So sine u, cosine v, and then for the sine difference, it is a difference, minus cosine u, sine v. So sine u minus v, sine u, cosine v, minus cosine u, sine v. Okay, anyone want to take a swing at number 2? What is the cosine of the sum? Cosine of u plus v would be, anybody? Okay, for cosine function, you keep it cosine. Cosine u, cosine v. But then you change your sign and make it minus sine u, sine v. Okay? There's your cosine sum function. Number 3, the tangent of a sum. Now that's a little different from sines and cosines, but it starts, at least the numerator starts a lot like the sine does. Well, no, it doesn't. Well, let's just do it. That would be tangent u plus tangent v. Okay? That's your numerator. Divided by your denominator, 1 minus tangent u times tangent v. Okay? So this numerator is a sum. The denominator is a difference of 1 and a product. Okay. Number 4. Sine of u plus v. Well, that's pretty similar to number 1 except for a SIGN sign change. Sine u cosine v plus cosine u sine v. And then number 5, cosine of a difference will be cosine u cosine v. It's a lot like, starts the way number 2 does, but this time it's the opposite sign, like it was opposite sign before, plus sine u sine v. Okay, and then the tangent of a difference, well, very similar to what number 3 was, except in number 3 the numerator was a sum, in number 6 the numerator is a difference. Tangent u minus tangent v divided by the denominator. Before in number 3 that was a difference, this is a sum. 1 plus tangent u times tangent v. Get to know them. They are handy. They are used a fair amount. Okay, so get to know them. Homework exercises here would be either 7 or 9. They're both at Calc Chat. Any of the odds 11 through 25, they're all at Calc Chat. 21's at Calc View. This is beginning on page 378, goes to 379 and 380. Okay, but we're on 378 now. So then after that, any of the odds 27 to 33, they're all at Calc Chat. 35 to 39, they're all at Calc Chat with 35 at Calc View. 41 to 45, all at Calc Chat, 43 at Calc View. 47 to 51, they're all at Calc Chat. 53 or 55, they're both at Calc Chat. 53's at Calc View. 57, this is now on page 379. 57 through 63, they're all at Calc Chat. 59's at Calc View. 65 or 67, both a Calc Chat. 67 is a Calc View. 69 to 73, they're all at Calc Chat. 73 is a Calc View. 75 or 77, both a Calc Chat. 79's at Calc Chat. Then on page 380, 81 or 83, both at Calc Chat. Those are true false. 85 is one of those error analysis. I really don't care for those too much, but they can be instructive. So 85 is at Calc Chat, should be there. Then any of the odds, either 87 or 89, both at Calc Chat. 91 or 93, both at Calc Chat. 95 should be at Calc Chat. 97 should be at Calc Chat. 99 should be at Calc Chat. And 101 should be at Calc Chat. Do they give you enough of those? I think so. All right. Now, any questions on 5.4? All right. Yuck, I just messed up something. Let me make sure everything's still functioning. All right, I think it is. Y'all can still hear me and everything, right? Okay, good. Thank you. All right. Moving on to 5.5, and we do have time, not a lot of time, but a little bit. So let me, oh, Azora, you raised your hand. What you got? You know, I really don't care, you know, as long as you turn them in homework problems. Okay, so right. Okay. Okay, one way you could tell is you can go to your I can't think what, YouTube videos. In the YouTube videos, every week I'll well, wait, does that show the weeks? Well, you can sort of piece them together because we have a class for every section, and in the title I'll put which sections. I'll say Math 113 sections 5. Today we'll say 5.4 to 5.5. So you can do any of the exercises in that. Just sort of figure out Tuesday, Thursday, Tuesday, Thursday, Tuesday, Thursday. You know, they'll just go down that way, and that'll represent each week. Okay, does that answer it well enough? I really don't care. Okay, just do homework and turn them in. That's all that matters. Okay. All right. So any other questions on 5.4? Looks like we've lost maybe a person or two, but let's move on to 5.5. All right, and we'll resume. Let's just do slideshow. I don't know why they're resuming or well, this is still the old one. So I'm going to get out of this one while I can and move on to 5.5, if it'll let me do it this time. Well, it won't do it, it seems like. So let me go to this again. This is such an aggravating thing. PowerPoint doesn't work well with anything. Okay, and here's 5.5. Let's start screen share there. Okay, and we'll go from current slide. Maybe it'll come up this time. There we go. Whew, finally. Okay. Section 5.5 is covering multiple angle and product to sum formulas. They also do one called sum to product formulas. We won't get there today, but we will do the multiple angle formulas, okay, or at least get started on them. So our objectives here are to use multiple angle formulas to rewrite and evaluate some trigonometric functions, We'll use power-reducing formulas to rewrite and evaluate trigonometric functions. We will use half-angle formulas to rewrite and evaluate trigonometric functions. Got an idea they like to either rewrite and evaluate trigonometric functions? Well, here's some more. We'll use product to sum and sum to product formulas to rewrite and evaluate trigonometric functions. And finally, we will use trigonometric formulas to rewrite some models, real-life models. Okay, very good. Let's start with our multiple angles. And frankly, these come directly from our sum formulas. That's exactly where they come from. Okay? Now, in this section, we'll study 4 other categories of trigonometric identities. The first category involves functions of multiple angles, such as sine of KU, cosine of KU. And they come directly from your sum angle formulas that we did in the last section. The second category involves squares of trigonometric functions, sine squared u, cosine squared u, tangent squared u, those kinds, and we will be reducing the squared to a linear. Okay, that's the second. The third category will involve half angle formulas, whereas this one did double or multiple angle formulas, this will do half angle formulas. So your multiple here is 1/2. And then the fourth category involves the products of trigonometric functions and later the sum of trigonometric functions. Okay, so let's start with the multiple. We'll start with the double angle formulas that come directly from your sum angle formulas. Now I'll show you what I mean by that. If you remember, I wish they had done this, it makes so much sense to me. What is the sine of, let's call it u plus v? We just did that in the last section. That was sine u cosine v plus cosine u sine v. Now, what if u was equal to v? Okay, so instead of this, it would be sine of u plus u, which is 2u. Happy sine 2u. Okay, and here, this would be sine u cosine u is equal to v cosine u plus cosine u, v is equal to u, so that would be sine u. What is that? That's 2 times sine u cosine u. That's what your double angle formula is for sine. It comes straight from your sum formula. No need to memorize it. Use it. Just get it right from there. Now, we're going to do something like that for cosine, but cosine looks more complicated, but it gives you more flexibility too. So I'm going to erase this if I can get my pen to show up here. And let's do the same type of thing for cosine. If you recall, cosine of u plus v is equal to cosine u cosine v minus sine u sine v. Now we're going to do the same thing we did before. Let's let u equal v. So this would then become cosine of u plus u, because u is equal to v. That's cosine of 2u is equal to cosine u times cosine u, because u is equal to v, minus sine u sine u is equal to v, so that's sine u again. Well, what is that? That's cosine squared u minus sine squared u. Now that looks sort of familiar, doesn't it? But it's not quite the same. Cosine squared u plus sine squared u would be 1. But cosine squared u cosine of 2u is cosine squared u minus sine squared u is cosine 2u. Okay, so that gives you the first of these. Okay, that's one way of expressing cosine 2u. But because of what I just said, that sine squared u plus cosine squared u is equal to 1. We knew that one, right? Okay, let's solve this for sine squared u. So sine squared u is equal to 1 minus cosine squared u. Okay, so for this sine squared u we have here, we're going to write this as cosine squared u, that's from there, minus, and then we're going to do, instead of sine squared u, 1 minus cosine squared u. 1 minus cosine squared u. If we do that, this gives you cosine squared u minus 1, minus a minus is plus cosine squared u, which gives you 2, I wish I had more room, 2 cosine squared u minus 1. And that's where you get the second one of these. But also, we could have written this as cosine squared u is equal to 1 minus sine squared u. I'm guessing we must be running out of time, are we? Oh my goodness, we just ran over. If you plug that in, you will get this form here. Okay? And then for tangent to u, you do the same thing, set u equal v, and remember tangent to u was tangent u plus v would be tangent u plus tangent v over 1 minus tangent u times tangent v. That gives you 2 tangent u over 1 minus tangent squared u. So those are your double angle formulas. We'll have to stop there and begin at example 1 next time. Now, we didn't actually do example 1, so we'll just leave homework assignments right where they were. Now, what this means is next time I think we'll finish 5.5. If we don't, we'll come awfully close. Certainly by Thursday we will finish chapter 5, or 5.5, and that means we're through with chapter 5. So either Tuesday or Thursday of next week, I'll give you the third test, which is the chapter 5 test. Okay? So you'll get it before Thanksgiving. Please work on it during Thanksgiving, because after Thanksgiving we just have 1 week left. Okay, and so we'll hopefully get started in chapter 6 next week, and then we'll continue in chapter 6 the week after Thanksgiving, and then is final exams week. So please folks, get those research papers in, preferably the month of November, so you can get that last bonus point. If not, you get it in the first week of December, you just get your score. If you get it in after the last day of class, which is the Thursday, first week in December, then you start losing points. So please get those done. Get your other tests in. I've got several of them printed but not graded. I've got a few of them graded that I have printed, but I don't have them in Blackboard yet. So I'm going to be working this weekend trying to catch up. I'll probably also be working Thanksgiving week trying to get everything caught up. Any questions? All right. Well, I hope you all have a safe weekend. The virus is exploding like crazy, so be safe, people. Don't let up your guard. Okay? Be safe, be careful, and we want to see you all on Tuesday. Okay? Yes, what's that?
So how many tests do you think we're going to have in your class, like at the end?
Okay, you will have, we've already had 2, both on chapter 4, first half of 4, second half of 4. I'll be giving you next week chapter 5 tests, and then at whatever we get covered in chapter 6, I'll give you a test, a very short test, just based on that. and then you'll have a comprehensive final exam, which will be very short as well, because you only have a week to do it, and I want to give you plenty of time. So we'll have 4 regular tests. The first 3 are pretty long, okay, I admit. The last chapter test and the final exam are going to be pretty short, and your research paper. Okay, that answer what you need?
Yes, sir.
All right, good deal. Thanks for asking. Any others? Okay, I'm going to stop sharing. I'm sick and tired of sharing now. And unless there's other questions, I'm going to end the meeting. Any others? Okay, y'all be safe, be careful. We'll see you on Tuesday. Okay? Bye-bye.